are some of the big things. And the big definitions I really want us to pay attention to here is an event. An event is always what we're looking for. The outcome is the results of your experiment or observational study, and the sample space is everything that brings it together, right? And that's kind of how we're going to do most of our probabilities. And we're going to stay mostly in the classic probability realm, which is the number of outcomes in the event, not even, divided by the sample space. So I always like to think of it as success total. So what we're going to do is we're going to redo this experiment, and then we'll come back and talk about it. So let's assign some numbers here. Figure out how to go back to the way. There we go. Cut out internet. My internet's kind of wonky today because of the weather where I live as well. So we'll see how well it's going. But I'm assuming everybody has at least some dice. And feel free to have the kids help if you want.
Well, I had one dice from earlier. I had to find another.
So we'll go Dylan, you and your crew roll the dice 10 times. Brianna, you'll do 15, Kyle 20, and then Emma 25. Okay. So what I want you to do is roll the dice, add them together, and count how many times you get a 7, a sum of 7. And then I'll be right back.
All right, you each roll one at a.
All right.
Chris, I feel like I've done this before.
Yes, I know. I got to come up with new things.
Didn't we do
The good
this?
news is most of the people that take stats afterwards will forget that we did this.
I was gonna say, didn't we do the same thing earlier in stats?
Yeah, so basically the next couple is going to be a review of everything we've done in statistics. Until we get to finance, you're not learning anything new.
Awesome. I'm excited.
Yeah, because we finished statistics here at the Z table, which is what we're doing right now in the stats class.
All right, I did mine.
Okay, how many did you get?
I got 1 7 out of 15 rolls.
Oh, wow. So 1 out of 15, okay.
We got 1 out of 10.
1 out of 10. Okay.
I got one. We got 3 out of 20.
And I'm still doing mine.
Yeah, I know the person that gets the 25 is always going to take a minute.
I was screaming at my phone.
And this is much better in the classroom.
Go
ahead.
So far, I haven't rolled 1 7, and I'm 1, 2, 3. I've rolled 11 times.
Oh, wow. In the classroom, I like to do this because I have 25 students rolling.
Yahtzee!
So you get a couple more chances of getting some of these results.
Oh, I rolled 1.
All right. And like I said, our problem is going to be small because there's only four of us participating. I guess I could have rolled 2 to increase the numbers a little bit. I guess what I can do is do the math real quick. So 1 out of 10, that one I can do in my head, 0.1. 1 out of 15. is 0.07. Five. Out of 25.
Three out of 25.
Not too bad. Everybody stayed pretty close, right? So you see, first group had a 10%. Group 2 there had the 7%. Then we had a 15 and a 12. So if we go back up here to our table, there's 36 different ways to sum a pair of dice, and 1, 2, 3, 4, 5, 6 different ways to get a 7. So 6 out of 36, or 1 out of 6, or about a 17% chance, 0.17 chance of getting a 7 according to probability. And as you see, comparing a 17% to ours, the 3 out of 20 was the closest, right? And if we all did this again, what would happen as the more times we roll the dice, we should approach 17%, right? And that is basically what the law of large numbers says, right? If you do a procedure or experiment over and over again, the relative frequency, which is what you all have calculated down here in these boxes, would be approaching the true probability of what we believe to be true is 17%. And this is how a lot of games are played, casinos, lotteries, all these things is we use what we know should happen, and then our sample statistics, which is what like you just did, will approach that if you stay long enough, right? And like I say here on this, 7 is the most common. This is how the craps table is played is in the casinos. All right, so if you ever play craps, basically if you roll a 7 or 11, you lose if the table is on. If the table is off, everybody wins. But if the table is turned on, then everybody loses their bets. So that's why if you're watching the movies, if you never played and everybody's cheering or someone has a hot hand, they basically have been rolling for a long period of time and haven't rolled a 7 or 11 yet, so everybody's winning. I usually do better when I'm not the one rolling playing, but we can always see. So that is kind of what these are. So if we come back to our table, which takes us back to our, I think it's chapter 3 when we did this, set notations, right? And this is what we kind of talked about last class, just a quick refresher, right? The outcomes of A. So if A is the event, you roll an odd number. There's 18 numbers. So 18 over the total of 36, right? And then I come down here. B is the 7. And then our outcomes of A and B, which means I have to be odd and greater than 7, which are just the purple numbers. And there's 6 of them. So that's where the 6 out of 36 comes from. The A or B is the more challenging one, which we'll get more to here in a minute. But that is basically all the numbers that are colored. And there's 27 of them. And then neither is our lovely complement. So if you do 1 minus, 27, not 1, sorry, 1 is 36. If you take the total sample space, 36 minus 27, that gives you the 9, and that's where these 9 events came from. Or you come up here and you count all the ones that are not colored. So this box of all the different ways to sum dice is our sample space. And then based on that sample space, we define some events, and then we can count the outcomes that meet these events. That's how all the definitions kind of play in with probability. Any questions on kind of like the breakdown in theory of probability? All right, so if we go on to 7.2 and 7.3, There we go. Hide all. So our book actually does really good at talking about this tree diagram, which mine, I got to rebuild. It doesn't look the greatest. But what's interesting about this tree diagram is I broke it down by majors, right? And so what I like to do here, and my start's kind of moved on me because things have moved around, but now it's on the computer, but that's fine. Start is where the tree becomes. And it's why it's called a tree is this is kind of like your branch. So let me see if I can actually, my drawing's gonna be horrible because I'm on my computer and I'm gonna try to use a mouse. So this will be pretty interesting. But the reason it's called a tree, right, is you have a branch off the main part of the tree. Horrible looking tree, but that's all right. So the tree is the start of the branch. And then as it comes out, then other branches break off. Right? And then it's these other branches that are breaking off are just like this. But the reason I like to put start is if the tree itself is the starting point, I can't get to this branch without going through the big one, right? And then I can't get through the other branch without starting at the big one and going to this one. So the key when you're reading tree diagrams and probabilities to remember, I can't just jump to a branch. I have to come back here to the start. So this is like a little one that I've made kind of for our class. So if we listed all the majors at CM, and then I found out how many of my students fall in these majors, we can create a tree, right? So Alyssa, she's not here with us today, but she's in the culinary, right? And I'm not sure what year group she is in, but then she would be put into one of these groups and say, I was also a culinary student, and I could be in one of these, and I could be in one of the groups. And then we have nursing, general studies, and it could break down more from there. But what a tree helps us look at real quick is it's a good way to kind of organize our outcomes. So we can do it like we did before where I listed a table with all of the different outcomes, or I could build this nice tree. And I like trees really when we get into conditional probability because it allows us to quickly see how things are linked. We've done some Venn diagrams, which we're going to do again today. And sometimes they work really well and other times they don't. And sometimes a tree works well and sometimes it don't. So right now, we're not into anything probability wise. Right now, all we're trying to do is list the different ways that we kind of have these outcomes. And so it's a way to just organize your outcomes. Counting is important because of finding probability. We want to have our success over total, and numbers can get big really, really fast. So there's a couple different counting rules. There's the fundamental counting rule, just means I take one, oh, let me draw, so now I'm writing on my thing. I take my M and I multiply it by my N. It just basically says I can multiply two numbers. And we'll do an example of this here in a minute. My factorial rule is this little symbol. And basically what it means, if I have, oh, I gotta get off draw. If I have 5 factorial, then that means I do 5 times 4 times 3 times 2 times 1. So let's see, 5 times 4 is 20. Times 3 is 60, and then times 2 is 120. So 5 factorial equals 120. But the key for something to follow the rule of factorial, it has to count down by 1 every single time. A multiplication rule example, right, is like flipping coins. Well, actually, we'll stick to the dice as we did the dice. A dice has 6 sides, and if I'm rolling 2 dice, right? So dice 1 has 6 sides, dice 2 has 6 sides, and 6 times 6 is 36. And that is exactly how many outcomes we had when we summed a pair of dice. Or pair of die, I guess, proper grammar. So what counting does is it helps us find our total really quick. And it can help us find our event if we're very careful in how we set up our events. So here's a little quick example. And it would be kind of, it would take our entire class if everyone was actually here to do this. But if we get 5 students, and I want to get the students to sit in order, right? So 1, 2, 3, 4, and 5. And if we were in class, I would actually have some of you come up in front of the class and we would do this visually so you can kind of see it. So now we get to play kind of stick figure here, right? So I have 5 students, and my first question, how many different ways can the students sit up here? So I have 5 chairs and 5 little students. Let's see if I can draw some stick figures. Do we have any art majors in our class? So one outcome, right? So we can have, this can be Dylan. And then Kyle, because we don't have enough students, I'll make this me. And then Brianna, and then Emma. There we go. So there's one way that the 5 of us can sit in an order. How many different ways can I move us around? Anyone have any guesses?
5 factorial.
Is it 10?
So I have a, let me get out a draw here.
Wouldn't it be 25?
So we have, I finally stopped drawing since it won't type for some reason. So I have a 5 factorial, I have a 10. 25.
No.
Right? So let's think about it. My first seat, now we're all standing, no one's sitting. This is just one outcome, but if all 5 of us are standing right here, how many choices do I have for this first chair?
You have 5 choices.
Right. I have 5 that can pick in the first chair, right? So 5 sit there. Now one person sat down, so how many do I have left?
4.
4.
4.
And then someone sits down. And we have our 3. And someone sits down. We have 2. Someone sits down. And we have 1. Every time it dropped by 1, so 5 factorial is the correct answer. Which we just calculated over here. So there's 120 ways to arrange the 5 of us to sit in the front of the class. All right, does that make sense?
Yes.
Good. So we'll leave that there. I'm slowly getting good with this Zoom thing. Slowly being the key word. All right, so now let's do my example here. How many different ways can we alternate between male and female? So I purposely made the males green and the females blue in this case. So how many different ways can we switch seats but separated by green and blue stick figures here?
So would that be 6?
So this is one outcome, right? So we have a 6. Anyone? Any others? All right. So let's go through the problem again. So how many people do I have to choose for the first seat? If I want male only.
3.
3.
3, right? So one of us sits down. Now we come over here to our female seat. How many do we have?
2.
We've got 2, right?
Yep.
So now we come over here. How many males do I have left?
2.
2. And then how many females?
1.
1. And then
1.
1. So 3 times 2 times 2 is
12.
12. So there's 12 ways to alternate between male and female.
So is that still considered factorial? You don't have to go down.
You can, because we could do this. It's a combination of factorial and a counter rule. So it is 3 factorial times 2 factorial. Because we have a 3, we have a 2 and a 1, and we have a 2 and a 1. So
Right.
now, why do we use counting, right? The reason is these problems have been really small, and it doesn't take long for the numbers to really pop up really fast. So if I bring up Excel, can everybody see the Excel?
No.
No.
Why didn't it automatically adjust my screen? All right. All right, if I change web browser, it's not going to change either. Did that change?
I got the web browser now.
Oh, okay, good. So we'll use Google. Google knows everything. So card deck, right? There's 52 cards in a deck.
Yep.
And I want to see all the different ways I can shuffle them. So every time I shuffle a card, it drops down by 1. So that is 52 factorial, right? Which equals whatever that big old number. So that is 8.0658,175. And then I add 60 more zeros to that number. I have no idea what that number is with 60 zeros, but it is a really big number. That's how many different ways I can shuffle a deck of cards before it repeats. Hence why we use cards in a lot of games, because there is a lot of different ways to do these things. And that's why we have to do counting. Something as small as a 52 factorial can definitely increase the number really big. And just think about your like ATM cards, right? Typically you need a 4-digit PIN, right? PIN for ATM. So if I do a 4-digit PIN and I go back to, I always like to draw things when they're small because it's a nice visual. So I have 1 number, 2 numbers, 3 numbers, and 4 numbers. Oops, I keep forgetting when I do draw, I can't move things. Nice. And typically when you pick an ATM, you get to get the numbers 0 through 9, right? So if I use my fingers and I count 0 through 9, that is actually 10 numbers. Can your PIN on your ATM repeat? Can you use the same number twice for your PIN?
Yes.
Yes. Probably shouldn't, but you can. So that means for this, I don't even need this box. I can just write these.
With
Insert, draw. So that means I have 10 numbers to choose for my first one, 10 numbers to choose for my second one, 10 numbers to choose for my third one, 10 numbers to choose for my fourth one, right? And this is not a factorial this time because they're not counting by 1. So this is the counting, I mean, not the counter rule, the fundamental counter rule, yeah, or I like to call it the multiplication rule. It is just 10 times 10 times 10 times 10, which equals 1 with 4 zeros, right?
Yep.
Yes.
Okay, just making sure. That's how many different pins you can make before you repeat for just a 4-digit pin. right? And now there's computer software and all that out there that makes it easier to hack people's information now. But before all of that, this is why we did it before all the computers, because if you have an ATM card, there's only one PIN that works, right? So there's 10,000 different ways to make a PIN, and there is only one PIN that is the right answer. So for someone to steal your ATM card and guess your PIN, they have a 1 out of 10,000 chance of guessing the right PIN for only having 4 numbers. And this is why winning the lottery is so hard, right? Because numbers can repeat. You have to get what? Powerball. You have to get what? 5 of them plus a Powerball. That's why it's so hard to win, because you're randomly guessing what the number could be, and you only have 1 out of all those chances of getting it right. So any questions on basically how we do some of these counting things? Like I said, I'll keep this all saved, so you might have to re-download the OneNote if you want to see all of my notes here, and they'll follow the things. So there's the digit for the PIN. So this is our ATM scrap paper problem.
I don't think you have to re-download it. I'm watching you on your OneNote do it on my
Nice.
computer.
Oh, perfect. Good.
Yeah.
Now, there is these 2 special types of counting, which is called permutations and combinations, right? And so the way permutations and combinations is you're picking something. So an example I always like to use for the class is, we'll say we're a full class. So say we have 25 students in our class. And I want to pick 3.
Riley, she's a female. She's a female. She's not a male. You can't fuck her.
Jeez.
Oh gosh. Sorry, I'm not on mute. My dog is totally trying to have sex with my female cat right now, and it's not gonna work because they're both females.
So the key difference between permutations and combinations is this whole with replacement. And this gets a little confusing. I'm not with replacement, without replacement. So basically, once you pick something, you don't put it back in. So very different than our ATM problem, where the ATM problem was we could have the same number. When we're doing a permutations and combinations type problem, you cannot have the number. So what separates these two, because they're both without replacement, is permutation order matters, combination order not matter. And what that means is not so much how I pick them, but once I pick everything I'm picking, if I change the order in the outcome, does that create a new outcome? And if the answer is yes, then that is a permutation problem. If the answer is no, then that is a combination problem, right? So an example I would like to use, I'm not going to try to write all this out by hand, so I'm going to just type it. I'm off a draw computer in my box. Come out here. So 25 students in the class. And I want to pick 3 of you to, not you, to help clean the classroom. Right? So I want to pick 3 of you to help me clean the classroom after class. Does it matter if you get picked first or last in this case?
No, it does not matter.
It doesn't matter. You just get picked. You have to stay and help clean the classroom. So that's what it means. Order doesn't matter. So this is a combination problem. Now, if I pick 25, I have 25 students, and I want to pick 3 of you to come to my fall class, talk about how great this course is. I only need one of you to come talk at the course. So if you get picked first, you're my primary. Well, the primary always seems to get sick or something. So if you get picked second, you're my alternate. And then because something always happens to the alternate, pick one more just to be safe as the backup, right? Now, does order matter?
Yes.
Yes.
Yes. Right, because whoever gets picked first, you got to find the excuse to get out of this thing somehow, right? And then if you got picked second, you have a little bit of a less chance of getting it, but you might need to come up with an excuse as well. And it leaves the person that gets picked third probably the one that actually has to go do the work. But it is order matters, right? So, this, for example, if we pick Kyle and Dylan and Emma, right, in that order, that means Kyle's the primary, Dylan is the backup, and Emma is there in case you two fail. Now, if I change the order, now Emma could be first, followed by Kyle, then followed by Dylan. And this means now that it has a different outcome versus up here, if we picked Emma, Dylan, and Kyle, it doesn't really matter. The three of you, even if I change order, you're the three that are back helping pick up the classroom. So does that make sense of what it means by order matters?
Yes.
And you'll always get more for permutations because right, the three students I picked to clean the classroom, I still only have one outcome. I've already created three separate outcomes by using the same students, and I'm not even done yet. There's more ways to continue, right? So that's what's, so there's always going to be more for permutations than there will be for combinations. So now the key is how do we do these calculations, right? So N is always your sample size, and K is how many you're picking. So if I put this into formula form, then it's going to be 25 factorial divided by, parentheses, 25 minus 3, outside parentheses factorial, which then equals 25 factorial divided by 22 factorial? Yeah. Now, what is interesting here, see if I bring it up because, no, I don't want that. TI, what is that calculator called? A 30x alpha? Images. Yeah, this guy here. This is what I think most of you have for a calculator, right? All right, as soon as the image comes up. I don't want to go shopping. I just want a picture of the image, people. There he goes, finally. So, this key right here that says PRB, right? If you click on that key that's PRB right now, you'll see the what will come up is an NPR, NCR, and the factorial symbol. Right? So the way you would solve the problem we just had here, or is my quantitative
This
reasoning?
does sound very familiar.
It does. You always put the N in first. So go back to your calculator and type in 25. Then hit the probability key. Then pick the one that says NPR. Hit enter. And then put in the 3. And then hit enter again. And what do you get?
13,800.
I'm glad.
How much?
someone's doing it.
13,800.
2,800 different ways. I'll do the calculations really make sure we're all together. So 25 P3. Did you hit the P or the C? Did you say 2,000 or 13,000?
I said 13,000. I think Dylan said 2,000.
I didn't say anything.
Yeah.
I had this on mute.
I think it's just the our laggy internet I'm getting today because of the storm, because my computer keeps telling me my internet connection's not optimal. So that's how many different ways I can pick 3 of you out of 25 using permutations.
So is it 13,800? Is that the right answer? Did I
It
do
is.
that right?
Why can't we do 25 factorial and then divided by 22 factorial on the calculator?
Yeah, you get the same answer.
600.
doing actual work over here.
What'd you do it on? So I just did it on my calculator and I got the same answer.
Yeah, I
Okay,
did
hold
too.
on. Divided by- So you're hitting, okay, so you're hitting NPR and not the factorial symbol?
Correct.
Yes. If you hit the factorial key, I did use the factorial key as well.
What is NPR?
NPR it does this formula for you so you don't have to. So in my calculator, I would do 25, then hit the probability key, then pick NPR, then put in 3, and then hit enter, and I will get 13,800.
Wait, 3, not 23? I mean, not 22?
No, you put in 3. If you use the NPR, you put in 3 because 3 is how many you're picking. If you actually use the exclamation point, the factorial sign in your calculator, then you put in the formula. So this is using the formula, which is what we have written here, or this is using the built-in function in your calculator.
Okay. Yeah, I don't think I've ever done that before with the NPR.
Yes. Now, if we redo the problem here, we can do the same thing that we just did up there, but instead of choosing PR, you choose CR. And if I do 25 probability key and CR,
Well, then I only get 2,300.
you
Yeah.
get 2,300. Now, does anyone have a different type of calculator they need help using? Most of us, I think, have the TI-30X Alpha. That's why I did that calculator. If you have the Casio FX300ES, which is the one I'm using right here now in my hand, the NPR and NCR are above the multiplication and division sign. So that's how the Casio does it. The Texas is under the probability key. So I don't expect any of you to do these formulas by hand. We should just use the little function key that's built onto your calculator, because it's the function's built into it, and you still have to know which one to pick to do the right formula, right? I have to know if it's a permutation problem, does order matter inside of the outcome, or a combination problem, order does not. Typically, a permutation problem is anything that's ranked. If I'm picking people to be president, vice president, CEOs, horse racing, first place, second place, third place, all those things have different results versus if I'm picking stuff for a committee or teachers to sign a class or how many homework questions I feel like doing, order doesn't matter in those cases, and all of those will be a combination problem. Does that kind of make sense?
Yes.
All right. Now, what I got here is a little example to do with using probabilities of picking people by our major. So we're going to have to make up some numbers just because our class is so small. But again, soon we have 25 students, right? If I can spell, that helps. And we'll say 25 students, 11 are general studies. Can't type today. 5 are in nursing. That's maybe just a comma. What other degrees we got here?
Life science.
Life science. So we'll say 3 life science. Kyle, wait, you're human services?
Yes, sir.
So let's see. 11 plus 5 is 16, 17, 19. So we'll do 4 human services. And Emma, you're accounting, right?
Yes.
So does that equal 25, 11, 16, 19, 23, 24, one more, 25. We'll do 2 accounts, 2 accounting. So there is our breakdown of students. So I now want to pick 5 students. Okay. What is the probability? Three of the probability exactly 3. Exactly 3. Man, I can't type today. Probability exactly 3 are general studies. All right, so there's the problem. Well, that should be a question mark. So if I pick 5 students, what is the probability exactly 3 are general studies? So remember, to find probabilities, it is success over total. So to solve this problem, it's easier to find the total. So to find total, total will be equal 25 students, and I am picking 5. So the first question is, this is a picking problem, so therefore I know it's either combinations or permutations. Which one is it?
It is combinations.
Does order matter?
No.
No. So it is combination. So therefore, I do 25 C 5, and that gives me Has anyone else got that number?
Well, how would I do? What's that math? 25 times. What is that math?
Oh, that's 25. Then hit the probability key on your calculator.
Okay.
Then pick combinations.
Is that NCR? Is the
And then-
combinations?
Yep, that's NC5. Yep.
Okay. NCR.
Yeah, I wrote it shorthand.
I
So-
gotcha. I gotcha. Okay.
NC
53 130. Yep.
What does the R
So-
stand for anyway? Just out of-
Yeah, R is what's on your calculator. Our book likes to use K, I think.
Like-
But it really, what it is, when you think about this, if you want to put it in words, it is sample size, N,
Yeah.
combinations, and then how many you are picking. And that can either be R or K, depending on what you're using, you know. But basically, what always goes first is the total size, what counting technique, and then how many you're picking. So the bigger number always will go first. So total was not too bad to find. What is a little bit harder to find is success. So if I want to be successful and back in my problem, so I'll put example by it because I'm slowly scrolling down here. How would I be successful? Well, to be successful, I have to get exactly 3 general studies. Well, I have 11 people in my class that are general studies, and I am picking 3 because because that's what the words exactly 3 means, right? The problem, though, is I'm going to put this in parentheses just to show it. This has to stay together. I'm supposed to be picking how many students?
5.
5.
5. But I've only picked 3. So I need to pick another 2 to get all my students.
Yeah.
Now, where do I get those 2 from? I get those 2 from everyone that's not general studies. So out of 14, I can do math in my head. And then I will multiply these numbers together, and that will give me the total different ways of getting a success. So my calculator, I would do 11, hit my probability key, go over to C, 3, and then hit my times 14, probability key, C, 2, and I get 15,015. So there's 15,015 ways to pick exactly 3 general studies out of my class.
Chris, is it okay that I'm not doing this along with you because I've already done it?
No, of course.
Okay. I was going to say, I know exactly how to do all this. I'll just use my stats notes.
No, yes. If you're taking stats right now, this is where we start statistics a while ago. So yes.
Okay.
This is the overlap between quantitative reasoning and statistics.
Well, I at least understand it.
That's good. So now that we know our success, and for all of you who are playing along, I'm hoping that you got 2015.
Yes.
Good. So now, again, to find the probability of exactly 3, man, I cannot spell exactly today. Then I do 15,015 divided by 53,130. I did success over total.
You should get 0.282.
Yep. So this equals 0.283. By just a rounding.
3. Yeah, 3.
6.
3.
All right. Which is, I should use the approximate sign, not equals, but that's 28.3%. So there's a 28.3% chance that using counting, I can get exactly 3 students that are general studies. So not too bad, right? Counting just is a quick way of finding the numbers I need to find success in total. The hard part of these is always getting the success right. The total is the easiest. That's why I always say start the total. But here's the little trick. All right, I want to draw this out as best I can with my mouse because I'm using a mouse. If I'm doing this out, we said we had 25 C5, and then up here we have 11 C3. I was doing good, so I had to do a 3. And then a 14 C2.
Come learn about probability.
Now put a little times.
Do your probabilities and success rate at your company.
Now,
Because I could take, when I go to school, I'll take math.
And I'll do it for you.
You'll do it.
if I add 11,
They only
and
have to take it
14,
one time.
I get 25.
I'm getting 2.
If I add the 3 and
So
the
do this and
2,
then stats.
Alex,
We want us, all the social workers, to take stats. That's all. Part of it.
then I get the 5. So this is a quick and easy way to check your math.
That doesn't make any sense to me, Chris.
If you add your ends on the top, you better get your big end on the bottom.
Okay.
If you add your pickings on the top, you better get your big picking on the bottom. In which they do, so I know my problem has been set up properly. Do one more?
Good.
I'm gonna draw. I keep remembering how to draw. All right, so another example. What is the probability of at least one life science? Based on the same scenario. 25 students in the class and I'm picking 5. So the good news, because we are using the same scenario, our total is still going to be the same of 53,130. If I can type, that'll help. 53,130. Because our total didn't change. What is changing is our success. Right? So, what is considered success in this case? What's at least one mean?
More than none?
More, exactly. So this is where the complement comes in effect, right? So success is more than 0, right? Which means in our case, I get 1 or 2 or how many did we say we have? 3? Or 3, right? Which means if I do it this way, 1, 2, and 3, I have to do these above calculations 3 different times, which is not wrong. You just got to do it 3 separate times and then add your answers together. However, because getting 0 is the complement, right? And if we go back to 7.1, our complement formula is here. Is it don't occur? I didn't actually give you the formula, did I? Did I not? Oh, well, let's add that. I didn't realize I didn't give it to you. So the complement formula, probability of A plus the probability of its complement equals 1. So there's the complement formula. When we come back here now, so if I want to do complement here to help me find my answer so I can do it quicker, this will equal 1 minus the probability I get no life science. So this equals 1 minus, what? So now how do I get success here? Let me do it this way. Success is no science, no life science. So going back to what we were doing before, I have 3 life sciences and I am picking 0. So this equals 3C0. But I still have to pick 5 people, right? So that means 22 people are not life sciences, and out of those 22, I need to pick 5. So my calculator now, I will type 3C0 times 22C5, which gives me 26,334. And then I take that over my total. So the probability of no life science equals 26,334 divided by 53130. So is that
Yeah,
0.
50%.
Yeah, basically 50% when you round everything, right? Oh, that's just weird. Because then we subtract it from 1. Well, I'm going to keep it not rounded just for a minute, just so we can see it's a little more than 50% when we subtract it from 1. So this is 4,95652. And then we do 1 minus 0.495652. And then we get 0.504, which is approximately 50.4% chance. So there's a 50.4% chance that I get 1 life science out of picking 5 students, which is, that one surprises me. It's that high. I feel like I did something wrong. This seems really high, but I guess it's not. If I messed up my math somewhere. 3 plus 22 is 25. 0 plus 5 is 5. All right. That's all right. Well, this is why we do probability. Sometimes you get numbers that don't make logical sense to you. I didn't think it would be that high of a probability, but I don't see any mistakes in our math. I figured with only 3 life sciences that we would have a lesser percentage chance of it happening.
I don't know. It makes sense. I mean, you only got like a 12% chance of picking 1 each time, or for the first time anyway. So
Yeah,
they're all pretty
okay.
low percentages.
That makes sense. All right. Yeah, because we are adding them together. Because remember, this does equal the probability of 1 plus the probability of 2 plus the probability of 3. So, but this is kind of how counting works. Combinations and permutations are the ones we typically use the most. But counting is basically ways of figuring out total outcomes, right? So scrolling all the way back to my top, we have our permutations, combinations. We got our factorial rule of how different ways of students could sit. Our fundamental counting rule of like rolling the dice. And a nice way to organize outcomes if there's lots of different options is a tree. Next class, we will start with this tree one, and we'll start assigning probabilities and building Venn diagrams from it. So today we basically just did probabilities using counting. Next class, we'll start doing probabilities without kind of doing counting. Any questions on anything we've covered today?